Where did we leave yesterday? Let's start from there. Where are you laughing?
She had an exam today.
You had an exam? And somebody else was there? Say please? Okay. Okay. Which course was this? Last year. Okay. So, where did we stop yesterday? What was the last topic we discussed? Density of states, exactly. And what do we mean by density of states?
Number of states available in the given range.
Exactly. So it gives me the number of states that are available, the number of chairs that are available, seats, right? And when I said that, but to get the whole, how many electrons or carriers are there in a certain energy, I first need to know how many seats are there, and then I need to know how do I fill it up. And how do I do that? What gives me that? A distribution function. That is what we'll do today. But before that, I just got these slides made yesterday for yesterday's lecture, but we did not go through them. This is exactly what we talked yesterday. That like if I am forming a solid silicon. So what we said was that there are 2 electrons in the S, 3s, and 2 electrons in 3p, which is not like that. By Moore's rule, this should actually go here. So we have 3 electrons in P and 1 in S, all parallel states, and those 4 actually hybridize. Hybridization means somewhere they become equivalent. So it's and then it forms this tetrahedral sort of atom. So the electron wave functions are distributed in a tetrahedral form, and then they form bonds and they form a solid. The moment I have neighboring atoms interacting, there is a splitting of the energy because of Pauli exclusion. Yeah? Pauli exclusion principle tells me that same 2 states cannot have same quantum numbers. And they were identical. There is spin quantum number, they are L, N, M, everything the same. So that's why they need to have 2 different energies. They cannot have the same one. And so they split. And so if I think of it, we will get a valence band and a conduction band, filled valence band and an empty conduction band. Right? So there is a band gap. Standard semiconductors. The details of the semiconductors will go after the midterm, because that is where we'll start with real semiconductors. As of now, we'll be talking of will flip from metals to basically solids. Yeah? And now the point is that we talked of crystal lattice earlier. So think of a lattice, fine? And we know that there will be some sort of anisotropy in the system, in the sense that I do have the A1, A2, A3 directions, and if I look in the 3 directions, they will look different. There's a different periodicity, depends on this crystal of yours. So what happens is, if I think of the band gap, and you really do the band gap, so we always work out something like this, right? The one I showed. I thought a valence band, a conduction band, and band gap energy. But it's not one energy in the system. It is the lowest energy that is there in the system. How? So if you think of it, if I have a lattice and I have some symmetry directions, right? So this is from here, if I come here, so this is your k-space. It's a x, y and z direction, not k-space, it's a k-space, and it defines you certain directions. directions are there. And they are different. So the band gaps you see along every direction will be different. When I say this is the band gap of silicon, this is the band gap of geometry, this is the minimum gap that is there in the system. So if I have something like this, I have certain directions and there is a moment between. So, and these names will be varying depending on the crystal structure. So let me go to the next one. Silicon. This is the lattice. It has a diamond lattice because you know, remember we have a tetrahedral. That was the seed of diamond lattice. And diamond lattice is nothing but it's an FCC lattice with 2-point basis. So you get 2 silicon atoms and place it in a FCC form. Then you will get a diamond lattice. Very important. Now if I calculate, so people do these DFT calculations and all to find the band gaps. So you calculate the band gaps for the different directions and finally you land up with a band diagram like this. Now there are multiple bands. Why? Because there are multiple bands. We just talked of, yesterday we told we are concerned with the band where I have filled band and then it is empty because that is where all the activities will take place and that is where I am calling it a band gap. But now I say that also is not a unique thing. There can be multiple band gaps. What I define as band gap of a system is the minimum gap that I have in the system. So if you think of it, the various directions I told up in the previous slide, you see how it is. So as you go from gamma to x, so these are the different directions. W is in this direction, L is center of this hexagonal face and so on. So these are the various nomenclatures that we have. And now if you go the sample this way in this direction, it will have that gap. But the point is that whether it will couple to your line, whether it's optically active, those are other lot of things that come into play. But end of the day, in this structure, there will be multiple gaps depending on the directions, and that is what is consolidated in this particular figure. So as I go from L point to gamma to x, so I am changing my directions. My band gap is, my valence band edge is changing, my conduction band edge is changing, so it is split here, and the gap is changing. Now we all know that silicon is an indirect band gap. Means what? That these are different k directions, right? I showed in the k space that these are the directions. So for a certain direction, actually this is the band gap, direct band gap for silicon. But this is not the minimum. The topmost point of the valence band and the lowest point in the conduction band, they don't fall in the same k value. They are two different k values. That's why I say it's an indirect band gap because I told you the definition of band gap is the minimum gap that I have. But for silicon, this minimum doesn't happen at the same k value. Not here, what it is. So something like this. So what implications does it have in the property of silicon? We don't make LEDs out of it. We make electronic circuits out of it. All your chip in your phone is silicon, but the display is never silicon. Display is any light emitting, gallium arsenide and so on, and now it's OLEDs, right? It's organic materials. But that is a different story. We'll not be into that. But the point is to emit light or to absorb light is something like a photon has to get absorbed or a photon has to come out. So you have all the conservation rules that are there. A photon will not give you enough momentum. So if I say I was here, electron was here, so I excited it to the conduction band. Then there's a change in energy and so I need a photon of that energy. So the system, the energy is conserved. And for a photon related transition, it has to be vertical because photon doesn't impart much of a k value. There is nothing, nobody to take away the momentum. Momentum also has to be conserved. So k, normally all optical transitions are vertical. Either if they are coming down and emitting a photon or going up and absorbing it. So now, but in our case in silicon, I know it has to go from here to here. So I have to change my k vector. balance this guy. I need a third particle, quasi-particle, to balance my momentum in this situation. Now, if you have something, an activity done by two people, it's easy to do. Now you need a third friend to come and finish it off. It's a more difficult task. You have to convince, you have to have the time for three of you and so on. So the moment you have more particles involved in the process, it becomes somewhat less probable process. And that's why optical, emission, absorption, everything is much, much poorer in silicon than any other direct band gap materials. So just contrast gallium arsenide. These are direct band gap. Means what? The topmost part of the valence band and the lowest part of the conduction band, they are all in the same range. So you just have to go from here to here, and it's one photon is enough for this. We don't need any photons, any other particle to carry away the momentum. That's why it is called a direct band gap, and it is highly optical reactive. It is very luminescent. I inject, think of it, in an LED, I inject an electron, I inject a hole, and they come and recombine. Yeah, hole, I hope you understand the concept of hole. You take it as a particle, it's an empty chair that goes around, right? So the electron comes, a hole comes, and they will recombine, give me a hole. Now in this case, when I inject it, the electron comes and goes to the lowest edge. The hole comes and sits here. They would not want to recombine because the momentum is not constant. They will combine only when there is somebody else to take care of them. But here in this case, the moment you inject, the electron comes here, the hole comes here. Hole is like a bubble, it will always flow. So hole lowest energy is here, electron's lowest energy is here. Reverse. And here in the same T value, they will recombine, give you a photon, and you get to the ground state. So that's why direct band gap materials are very optically reactive. They do absorb photons, they emit photons with high probability, but not really. But the whole idea is this, that this is the band structure that we have, and from these structures we can find out which material will be most suitable for your purpose. But electronically, yeah, silicon is very good. And silicon is abundant, it's cheap, so there are other factors why we are using silicon. Silicon is sand. Right? So, abundant. Okay. So that is the structure of gallium arsenide. That is also a diamond lattice, but here it's more like it's a alternating gallium and arsenide. That's our structure. It's actually zinc blend structure. Diamond lattice with alternate atoms, two types of atoms is called zinc blend, zinc sulfide. And that is the crystal lattice. ZNS, exactly. Okay, so this was something as a continuation of what we were already doing yesterday. And still we go further. So yeah, I gave you homework yesterday. Calculate the density of states for the we did the 3D system, right? So what about the 2D, 1D? Did you solve it? Nobody did. I left the class 5 minutes and they say they finished the class and go. What happened to that? It's okay, no problem. But we all know. So for 3D, so the density of states we write like this, right? G, location. For 3D, it was proportional to energy to the power. For 2D, so yeah, it's actually constant. It's independent of it. Constant in the sense independent of energy, no energy difference. And 1D, yeah, it just goes as in a half it goes downwards. So we think about minus half. And for 0D, delta E minus E naught or whatever, wherever you have the energy of the system. So these are the density of states. Now these are the number of states available at a given energy. So this is what is plotted here. This function is plotted this way. So this is the indica half, which we have already done yesterday. For quantum belts, it's independent, so they will be like flat. But it looks like stairs because it's like one transition and then the other transition starts. So in a quantum belt, it's this slow quantum. Can you see it like right here? So if you have a quantum belt, it's a so if I plot some energy and let's say I will think of your absorption. Let's see. You can see from that side. So you have not absorption. Now if I have very low energy, nothing happens. There is no transition. Yeah. I mean there's very less. In the XY plane it's a confined thing. It's very less transition. The moment I hit one of these, I start to see strong absorption. And then I change the energy. So this is my, let's say this was E1, this is my E1. So from E1 my absorption should start. Suddenly it starts, this transition. And it doesn't change with energy. Because to the system it doesn't change, but it is still absorbing because it is taking that energy in the XY. In this direction it is a quantized thing, so it starts, but it will keep on absorbing till the end. But by the time I come to this energy, E2, my second transition starts. So as I am increasing the energy and I come to somewhere E2, I have another step which starts and it goes. So each of these steps that are shown here is the commencement of one of each of these transitions that start. This is the lowest energy transition, then the second one, the third and fourth. That's how the states are. But I have given you absorption. Absorption is the measurement which tells you how many seats are there. Because I don't care about who is sitting there. I rather want empty seats. I just tell you, I will send you to this excited state, will you absorb or not, how much is the probability. So absorption plots will replicate your density of states. Emission mode. Emission will have something else also because I'll come to that later on. But absorption will do optical properties. The thing to remember is density of states show up in absorption spectrum. Clear? And then, of course, E minus half is for nanowires. It goes like this. So when you hit that, so in the nanowire you will have, let's say, the confinement in X and Y, only Z direction it can. You can plot it that way. So you have something like E minus half, which is this volume curve, and then the delta function for the delivery. Any questions on this one? No? Shall I go ahead? Okay. So I told you that absorption shows density of states. I just picked up the point of it. A very standard plot. Yes. S and Y you can move. So the buffer energy is going there, right? Because here it is only line to line. Certain E1 energy. But then it should not absorb after that. Where is that energy going? That is the in plane. And for the whole system we know this is how the density of states is. Okay? Because for dots, for quantum dots, because they are confined in all directions, there are only certain energies that can happen. But if I am allowing it to move in a certain, direction, so let's say in the XY plane, then I can have other energies also. Because as I am shooting the higher energies, it is absorbed. Because where is that extra energy going? It's going to the in-plane line. Fine? Let's look at this first. This is much more complicated and that will rather do when we do the detailed semiconductors, but I plotted. This is the absorption plot of gallium arsenide at room temperature. This is bulk, this is a polymer. Okay? Before we get into it, bulk means what? The thickness is large enough that there is no quantum confinement. What dimensions bring, how small should it be to get to a quantum confinement? Particle means? No. What is the size of the atom? The size of the atom to forget it. XRD we have done. We know typically what is the spacing and so what should be the size of the atom which is even smaller than that. Right? So we are not getting to that. So what I need to do is, what will I tell you, when do I start seeing confinement? When the particle can hit the They feel that the wall is there. The moment I'm restricting the particle, it starts to slip. Stronger the confinement, more is the splitting. Quantum well. Narrower the quantum well, more is the splitting. That is an inverse of density. But, so de Broglie wave. We do have a length scale assigned to a particle with certain energy. It's a de Broglie wave. Now, if the length scales of confinement or your nanostructures are of the dimension close to the de Broglie wave, then the particle starts to see the confinement. So it has to be some tens of nanometers. So here they do for 10 nanometers. You will see confinement in 20 nanometers. It's not so, robust number that you have. But of course, then the separations will come closer because the splitting will be less if it's a broader one. So you have to decide. There is one more concern. Room temperature, KBT. So if I have a very broad quantum layer, such that my levels are very close by, and thermal energy is enough to excite the particle from here to there, then we won't see any discretization because thermal energy has blurred the whole picture. So KBT, how much is it? How much is KBT in room temperature? 25 millielectron. So the separation has to be somewhere more than 25 millielectron. That also brings us to numbers like this. The spread. So basically, if my discretization, so when I solve a quantum well problem, we put some delta E, right? Yes, E1 minus E2, the splitting of the levels. If the splitting of the levels is less than the room temperature energy, then thermal energy is enough to blur. So you do an experiment, you won't see any confound. You won't see any feature because everything is flat. Because thermal energy takes care that it doesn't need your photon to do the excitation. It's already blurred. It's overlapping, it's blurred. So we normally even sometimes draw the states, and if you want to show, it's a blurred thing. It's a band because the KBT is an energy that can be there. It's a kinetic energy. Right? So here, in this picture, this is the absorption of a gallium arsenide. Bulk means half. So it should go something like this. What we see here, no features as such. There is a little something I'll tell you, I'll come to that. And then you do for quantum well, it is totally different. And now you can see the steps, right? Other than the peaks and spikes you see over here. So I see the density of states in the absorption state. Same thing down here, but this is more elaborate. So here we see the energy levels of this, just like the one I did here, this here. These are the various energy levels we have. Now, there is something called heavy hole and light hole. So holes are of actually three types: heavy hole, light hole, and space. So that we will do more in details when we start the semiconductors after. But the idea being that I had 4 levels in the outermost shell, 4 electrons, right? In all these semiconductors, there are 4 electrons. So somewhere these electrons have to be active. So the states that are formed from these 4 electrons will be 4 states. 3 of them in the valence band, 1 is in the valence band. So that will come into this. Okay? So here, as of now, it's not just one valence band. It's named instead of staying as free electrons and holes, which just run and come and bind into the photon or you excited, you actually have states which take care of the Coulomb interaction. So when you write the Schrodinger equation, it's not just your periodic potential at this. You also have to say there's a Coulombic interaction, and then it becomes a system of two particles, not electron alone and hole alone. So that is called excitons, and they are like, yes. So here this one is, these two are L equal to 1, capital LIGO, capital LIGO. So it's like step, 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 like that. Okay. So they are saying that every L will have, this is heavy load 1, light load 1, heavy load 2, light load 2. So they are coming in pairs like that. So, but apart from it is practically two steps. Light load is much closer, but the separation is increasing and is going far, further. But on the step there is a spike. So this is a exciton for the heavy load. This is the exciton for the light load. Okay. So if I just blow this picture up, one of them at least. What I said was, this was my density of states, where this was my E1 energy. This is the energy axis, and let's say this is my density of states for a 2D system. Okay, so for a 2D system, this is supposed to be my absorption. That means that at this energy, this is the amount of states I have, and that's why if I allow it to absorb, it will absorb it back to the gravity. But I said no, this is not the complete picture. This was considering only the band theory where electrons and holes are developed. But they are having a Coulomb interaction. So what happens to that? Coulomb interaction means excitons. Excitons are nothing but an electron and a hole. Quite like a hydrogen atom. The potential interaction is like a hydrogen. Hydrogen is also nucleus and a single electron. So just like you have SPDF, in exciton also you have SPDF. So for this feature came from something like this, right? If I had the quantum bed. And you had, say, these two states, and this was the transition I was talking about. First one confined level here, one confined level. But each of these levels, if you consider the excitonic interaction, it has a certain connection energy in that, and these are these SEDF levels associated with that particular level. So now, instead of having this transition, this will also have this thing. It will go here. It can. And that shift, so the difference in the length of this arrow is nothing but the binding energy of the exciton. Just like the binding energy of hydrogen. Rydberg constant. So in this picture, because it's a very stream system, it's not like a pure electron and a hole. They have a lot of other charges here, so there's a lot of streaming going on. So typically the binding energies are not very large. MeVs for bulk, tens of MeVs in confined structures. So in a bulk, because they can go around, they are not very close by. This interaction is very less. That's why you don't see a spike here. The exciton has broken. They are far off and you don't have much of this. If you pull this, you reduce the kinetic energy of the particles, you pull the whole system, scattering everything you reduce. Then you start to see a bit of a signature in exciton even in the bulk. But if its thermal energy is enough to break the exciton, thermal energy is more than the binding energy of the exciton, then you see free carriers. So free carrier consideration is good enough. But if you pull the system, then the thermal energy is not enough and you see the existence of exciton. So there was a lot of study in the beginning as to formation of excitons and then how they break up and so on. And this becomes very important in photovoltaics. Why? Because in photovoltaics, we absorb light, create current. If it's an exciton, it's a neutron particle. It has an electron and a hole, it's neutral. Exciton, if it moves, bulk materials, room temperature, thermal energy is enough to break the exciton and you don't see much of an exciton. For quantum beds, this is all done at room temperature. Even at room temperature, I do see the spikes which is associated to these transitions. So practically it's an exciton. It's very difficult to draw it this way. Because exciton is a two-particle system. You cannot draw it this way. So normally when you draw for excitons, you just write S0, S1 and something like this. Just like in hydrogen atom. You don't draw here. All I'm saying is every transition will have a bunch of exciton associated with that. The lowest one will be the strongest and you see one spike. If I had enough resolution, maybe I could have seen some fine structure, but normally those are so close by you won't see it. But you do see a spike associated with exciton. And as I said, it's a Coulomb interaction, so if I confine them in a small place, the Coulomb interaction becomes stronger. So when I go from bulk to this 2D material, I have some 10 MeV around, 10, 12, 15 MeV of binding energy. So room temperature, it still gets difficult. Low temperature, it gets better because the excitons don't break. So they see the signature of the excitons. From 2D, you go to 1D nanowires. Again, bring them even closer. I don't allow them to move so much. So the Coulomb interaction becomes stronger. Up to quantum dots where it becomes like 25, it's above, it's anywhere delta function, but you have to consider the Coulomb interaction. For molecular systems, as I told earlier, that when you do an excitation, it stays in the molecule. It can hop, that will be needed eventually. But the moment I excite, there's an electron and the hole in the same molecule. They will have very high binding energy. And that creates a very big problem in using organic semiconductors in photonics. You are absorbing, they are absorbing, but they are not creating barriers. Okay? So, here, this picture, can you just tell me what? So, the density of state shows up in absorption spectrum. For 2D systems, it is independent of energy, so it looks like steps. For first transition, then second transition adds up, and third transition adds up. There can be light hole, heavy hole that we are not discussing right now. But there are signatures of excitons because we have come for 2D, so I have already started to confine. So the Coulomb interactions are getting stronger. So I start seeing some features associated with the excitons which are nothing but not a free electron hole pair, but a electron hole pair which has some Coulomb interaction and we have a little binding energy shift in the electron. And the feature looks like a sharp, like a hydrogen atom, like not hydrogen atom. Ideally, I mean, it has a sharp spike. Is it clear? Any questions? So, just another thing. The excitons typically have, there are one more type, but barrier Mott and Frenkel excitons. So the idea being that this is just type, because I'm talking of excitons, I just thought of flashing this slide. So Frenkel excitons, for example, this wherever they create, they are generated, they stay nearby. So molecular systems, for example, you create an electron and hole, they are very tightly bound. Frenkel excitons are very tightly bound. They stay in the system, in one molecule or where they are being created. There is another type called barrier Mott excitons, which is like, they are hard, they can move around, there's certain radius, beyond which of course the interaction is nearly non-negligible. But within a certain radius, it still has to be the bigger radius exciton, their binding energy is less, because they are hard. In crystal structures, this is typically the one that happens, because they don't need to stay in the same. Spatially, they have a extended wave function, so the electron can move away from the hole that it is created. But for molecular systems, it is strongly. Okay, there's another called charge transfer excitons, which we are not doing now. That's a little more complicated, not complicated, it's a different picture. We'll see if we do organic, we may. So now I'll do a little of this. So I told you that density of state is there, and we also need to know how distribution functions. We all are familiar, we have done SAT some point of time. So we are all familiar with Boltzmann distribution, Maxwell-Boltzmann distribution, and efficiencies. empty statistics. So think of it, I have two particles who come, they scatter and leave out elastic. Okay, so I have E1 energy, E2 energy, they go out with some energy. First and foremost, elastic scattering, so energy conservation is there. So I can write E1 plus E3 plus E2. And now I say that I want to find out the probability. That is the distribution function. How many particles are there with energy E? That is my probability, right? Distribution function. So let E be the, so PE1 is the probability of a particle to be in energy state, in a state with energy E. Similarly, PE2, P is a distribution. It has nothing to do with it. So to make this happen, I say that the probability for this to happen is PE1, PE2, because I need a particle in E1 state and E2 state. So the product of these two probabilities is the probability of this event will happen. Because it's in thermally, it's in thermal equilibrium, so the reverse process is also true. They are just happening in both directions. So the forward process and the reverse process will have equal probability. So this probability should be equal to PE3, PE4. Okay? It's a Boltzmann statistics. It doesn't require Pauli exclusion. There are ample states there, high energy. We normally say high temperature is Boltzmann. Classical, where I have a lot of states, lot of particles, there we don't need to care about. And for those, so I don't care about empty states because I know there are ample states. So this statistic did not take care of that. And these are the two equations I have to obey. That energy conservation and also that the probability should be this, the probability of the forward and the reverse solution. Then I am putting it as a trial solution. We put the Boltzmann distribution function as a trial solution. Okay? We all know about that. So PE is sum A exponential A, right? Boltzmann distribution. You see, this obeys this with this connection. Think of it. PE1, so this would be exponential E1 plus E2 and E3 plus E4, and those two are equal number. So this solution is a trial solution. Suffices this and this. And so this is the Boltzmann distribution. Okay? We know it. We have not derived it. I'm just saying that it obeys the statistical, the statistics or the assumptions in the statistics that we have. Is it clear, everybody? How many derivability you will take? Every statistics for the same thing. Now we do for this was B statistics. Sorry, MB. MB statistics. Now we do MB statistics. Fermi derivative distribution. In Fermi derivative distribution, we think of, we include Pauli exclusion in the system because fermions will, have this, there's no condensate in those fermions. So for every statistics, we include the fact this is still valid, always valid. But here, I'll make a little change that not only I need carriers in E1 and E2, and there are limited seats. Okay? I also need empty chairs at E3 and E4 for the forward. So if I want to go from here to here, I need filled states in E1 and E2, and I need empty states in E3 and E4. Only then you can scatter and fill those states. This scatters to E3 and this scatters to E4 or whichever. So I have condition, they become E3E4. So for the process to happen, I needed empty seats in E3E4 and fill states in E1. So this equation modifies to not only I need fill E1 I will need 1 minus E3, 1 minus E4. This is the probability of a state with energy E3 to be filled. So the probability that it will be empty is 1 minus that. So this tells me E1 is full, E2 is full, E3 is empty, E4 is empty. In one direction. We can write the same in the reverse direction. And equate it. So equal to the other way around. That I guess you can write E3, E4 and the rest of it. E1 and E2. Both ways it should be equal. So now with this relation, the trial solution will be different. So now the condition is this and whatever comes out will be this relation. Yeah. With this, my statistics should be I hope this is there. This is the empty statistics trial solution. Yeah. If you now you give a try at home, plug this here. You will see the surfaces if you have this condition. The same way we have done for the Maxwell-Boltzmann statistics. It's not a derivation, it's just checking the function that we have very familiar with. So the moment we include Pauli exclusion or we have limited chairs, so we need to consider that the final states are empty for the process to happen, then it automatically converts to empty states. There will be minus E minus EF. So EF is, I will come to A. A will give you A. It is E. End of the day, it can't go the other way around, right? It has to go to the Boltzmann statistics village at a classical village, right? So this will become E minus